This is the first lecture video for Chapter 7. Now, Chapter 7 is the shortest chapter of the entire semester. I'm still going to break this into 3 lecture videos, even though it's not a very long chapter. Just hopefully this time the videos will be shorter. It's all about the periodic table, so I strongly suggest having a copy of the periodic table in front of you. Just a reminder, the periodic table can be found on the back of the front page of any exam you've taken so far this semester, other than the one that you took on Mastering Chemistry, as well as on the back of the back inside cover of your lab manual. And there are also in Chapter 6 Canvas page, there's a copy of the blank periodic table. I also gave you copies of the periodic table earlier in the semester. Okay, so I would have that in front of you. The good news is when we're talking about Chapter 7, you know a lot about the periodic table already. You know what the symbol in the box stands for. It stands for the name of the element. You know what the whole number above the element symbol in the box of each element box stands for. It's the number of protons, and you know the number with all the decimal places after it underneath that is the average atomic mass. We also now, after Chapter 6, know why it's in that funky shape, because they broke the periodic table into the S block, P block, D block, and F block. So again, we know a lot about the periodic table already. There's other information that's a lot more subtle, and that's what we're going to be learning about in Chapter 7. But first, again, we have some background information we have to go through. So initially, it's just letting you know that we kind of talked about this in Chapter 6. The periodic table didn't always look like this. There were several different versions of the periodic table before we got to this one. And initially, the periodic table was not grouped by atomic number, which is what it is now, the number of protons. It was at one point grouped based on the average atomic mass. So they looked at the other number in the box and put them from smallest to biggest. This chart here is just kind of fun facts. It's color-coded based on when the elements were discovered. So some of them ancient times, some of them Middle Ages, and some of them more recently. There's a block of them down here that our textbook doesn't show, but all the elements in that block have also been, we're going to call it discovered, but in real life it was created. These were lab-created elements. So just stuff is still happening with elements is kind of the point of that. What's kind of cool though is once the periodic table is kind of in its shape, they were able to predict elements that hadn't been discovered yet. So if we go back, obviously at every moment in time there hasn't been the entire periodic table. There were elements that hadn't been discovered. They already existed in the universe. They existed on Earth. It's not that they weren't there. It's just that humans didn't know about them yet. So there were gaps in the periodic table. And scientists were able to figure out where those gaps were and even predict what properties the elements that they have not discovered yet would have. So we're going to be looking right here. Silicon was discovered before germanium. So for a while, germanium was a block that was like an empty spot on the periodic table. I guess I'm coloring him in. Okay. So this is the predictions of what scientists believed germanium would behave, like what its properties were, how it would act. So the first column is that they expected the atomic weight to be 72, the density to be 5.5 grams per cubic centimeter, which grams per milliliter is the same thing. We have a specific heat and melting point color. Like these are all the things they predicted. The last column says the observed properties of germanium. This is what germanium what its real properties are once they discovered it and they tested it. If you look, things look pretty close. The melting point, they kind of they went easy on this, and they called it, when they predicted it, a high melting point, but 947 degrees Celsius I think qualifies for that. They even predicted the color, and they were pretty close. It was gray. It was just a lighter gray than they expected. But all the way across the board, they predicted what germanium was going to be like before they even had a sample of germanium to test. These are the types of things we're going to be looking at. You're not going to be predicting what's happening with new elements, but we're going to look at the trends on the periodic table, how they could predict this. And so earlier in the semester in Chapter 2, we talked about the beginning stuff with the periodic table. We talked about groups, which are columns on the periodic table, and periods, which are rows on the periodic table. And groups, which are the columns, can also be called families because they have similar properties. Like elements in the same column have similar properties. And so some of that is what they used to predict this stuff. So again, it was initially, the periodic table was based on average atomic masses, and at the time it wasn't, I don't think, average, just atomic masses, because they weren't quite aware of the isotopes yet. And then once the nucleus was discovered, the number of protons could be determined, and that's when things changed. So periodic table is based on protons right now. So periodicity is just these trends that we're going to be talking about. How could I predict what's going to happen? Again, we're not going to be predicting based on numbers, but I'm going to give you two elements and say, okay, based on this property, tell me which one would be higher or which one would be lower. Those are the types of things we're going to be doing. So these are the trends: the size of atoms, the ionization energy of atoms, the electron affinity of atoms, the metallic character of atoms, and then some chemical property trends, which means certain groups, we're going to learn things that those groups do that other groups don't. These first four, we're going to be looking at those trends, and I could ask you to compare two elements on the periodic table or three elements on the periodic table and rank them based on their size or ionization energy, electron affinity, or metallic character. Good news is we're also going to talk about what those words mean. I'm hoping size is not a terribly difficult one, but at least ionization energy and electron affinity are new terms for us, so we will talk about those. In this video, we're going to focus on the size trend, and we'll talk about the next three on the second video, and then the group trends will be on the last video for chapter 7. So before we can talk about size, we have to look at the atom a little bit more. So we know the nucleus has protons and neutrons. The electrons are not in the nucleus. They are in their atomic orbitals, those s orbitals, p orbitals, d orbitals, f orbitals. All the stuff we talked about in chapter 6, that wasn't a lie, and we're not forgetting about it. So we know that electrons are in their orbitals. So what we're going to be looking at is the effective nuclear charge. So that before we talk about the effective nuclear charge is just what the charge is in the nucleus. So remember, the nucleus is protons and neutrons. Neutrons do not have a charge. So protons are what makes up the nuclear charge. So if we have like an element of carbon which has 6 protons, its nuclear charge is positive 6. If we have bromine which has 35 protons, then its nuclear charge is positive 35. So that just the straight up nuclear charge, just the number of protons with a positive sign in front of it. The effective nuclear charge is when we look at more specifically how much of that positive that the nucleus has can be felt by certain electrons in their orbitals around that nucleus. And the reason why they're not the same is because if we're looking at a valence electron, so an electron in the highest energy level, an electron that's the furthest away from the nucleus, it's being shielded by other electrons. In other words, electrons are in the way. It cannot feel the positive charge of the nucleus because there's stuff in the way. Think of it kind of like if you're in a forest, the sun is out, there's no clouds in the sky, but you're surrounded by trees. So the sunlight is being filtered. You're not getting all of the sunlight because the trees are blocking some of it. That's what's happening here. The electron is being shielded or blocked from the positive charge, the radiant sun of the nucleus, which is just a positive charge for us. And the other electrons are blocking some of that nuclear charge, so that outside electron is only feeling part of it. So how much it actually feels is the effective nuclear charge. We know electrons are all negative charges, so they repel each other. So they're not super close together, so they're spread out, but they're still going to block some of the positive. Okay, they're being attracted towards the nucleus though. So that's why the electrons are spread out and not all the way stuck to the nucleus, is because of the repulsion forces between the electrons are keeping them spread out, even though they are being attracted towards the nucleus. So the effective nuclear charge, the symbol for that is the capital letter Z with EFF as a subscript. Z, capital letter Z, is the symbol that we used to stand for atomic number back in chapter 2. So atomic number is the same thing as nuclear charge. So just regular old Z is the atomic number, which in this chapter we can say it's the same thing as the nuclear charge. ZEFF is the effective nuclear charge, the amount of the charge that's felt by whatever electron we're looking at. So the equation for this is not terribly difficult. The effective nuclear charge is equal to the nuclear charge, which is just the atomic number, which we can get this off the periodic table, minus S, which is some screening constant. There's a whole bunch of set of rules on how to calculate the screening constant, and we're not even going to look at those. Okay, so the screening constant, as far as we're concerned, is going to be, so I'm going to write S equals the number of core electrons in that atom. So at the end of chapter 6, we had two vocab terms, valence electrons and core electrons. Valence electrons are the electrons in the highest energy level. And core electrons are all the rest of the electrons. So the electrons in all of the other energy levels. Okay. So the trend for effective nuclear charge, as the effective nuclear charge gets bigger as you go left to right on the periodic table, and it increases as you go a little bit as you go down a group. As far as we're concerned, we're not going to see much of that increase going down a group because we're simplifying our screening constant. So we're gonna practice this, but that's why as we go, there's a difference between 2s and 2p, and the electrons in a 2p are going to feel something different than the electrons in a 2s. But again, we're going to kind of go with a simplified thing. So let's do an example. I'm going to pick nitrogen. We're going to do the effective nuclear charge for the last valence electron in nitrogen. So first of all, I'm going to say, well, nitrogen has a Z value of 7, which means it has 7 protons. Okay. To get my S value, I need to have the number of core electrons. So what I'm going to do then is I'm going to write the electron configuration for nitrogen really quick. So 1s2, 2s2, 2p3. Okay. So the number of valence electrons are the electrons in the highest energy level. So our energy levels I see are 1, 2, and 2. So which number is the biggest? Between 1, 2, and 2. 2. So the electrons in the second energy level, which are these, are the valence electrons, which means anything left over are the core electrons, and that's going to be our screening constant. So to calculate the effective nuclear charge, I'm going to take 7, which is the nuclear charge, the atomic number, minus 2, which is the screening constant, which is really the core electrons, and this is whole number subtraction, so 5. So the electrons in the valence electrons on nitrogen are only feeling a positive 5 pull towards the nucleus. So I'm going to do oxygen now. Same idea. Oxygen has 8 as its atomic number, and its screening constant, which are the core electrons, well, I'm going to write the electron configuration. 1s2, 2s2, 2p4. Okay, so S is the number of core electrons. So the electrons that are not valence electrons. Valence electrons have the highest energy level. 1, 2, and 2. So these are my valence electrons, which means everything that's not in that box are my core electrons, and there's a 1s2, so 2 electrons. So to calculate this, the effective nuclear charge is going to be 8 minus 2, which gives me 6. So oxygen's electrons have a higher effective nuclear charge. What that means is the outside electrons in oxygen are feeling a stronger pull towards the nucleus, because remember, opposites attract, right? And the nucleus is positive, electrons are negative. So if the electron is feeling a +6 charge, it's going to be pulled in, it's going to be sucked in closer to the nucleus. In oxygen, where the nitrogen electrons are feeling a +5 charge, they're still attracted towards the nucleus, but the nucleus, I guess we can think of it like a magnet. The nucleus magnet is not as strong in nitrogen as it is in oxygen in terms of the positive charge that it feels. Okay, so this is going to impact the size of the atom. So I'm kind of jumping ahead a little bit, but the fact that oxygen has a higher ZEFF, its answer was 6, nitrogen's was 5, so 6 is bigger than 5, that's why it has the higher effective nuclear charge. That's going to make the electrons pulled towards the nucleus more. So that means if the electrons are pulled towards the nucleus more, what we're going to see is it's going to be a smaller atom. Everything's going to pull in a little bit. So this one has a lower ZEFF. So the electrons are not pulled as tightly to the nucleus So it's going to be a bigger atom. The electrons are more spread out. They're not pulled towards the center as much. So we had to talk about the effective nuclear charge because the next thing we're going to do is talk about the trend for size. And this is going to show us, this is going to explain why the trend works the way it does. Okay. So before we talk about the trend, we first have to talk about how the heck someone would ever figure out the size of an atom, because we can't see these buddies with our eyeballs. We also can't find the electrons in space because electrons are super tiny. They're like 1,500 times smaller than a proton or a neutron, so they're very, very tiny. So we can find the nucleus of an atom. If you remember all the way back to chapter 2, the Rutherford model of the atom, he put a piece of gold foil and then threw alpha particles, little things, at it. And some of those alpha particles bounced off the nucleus. So it's possible for us to find the nucleus because they did that before with the Rutherford model of the atom. So how we find the size of an atom? We're going to take an atom of any element, so I'm going to go with oxygen again, and we're going to force it to bond to another atom of the same element. So O becomes O2. So that's what this picture is showing. There's the blue circle, those are the two atoms. The black dots in the middle are the nuclei, the nucleus of each atom. So they're pretty much, the way we figure out size is we're going to do the Rutherford model of the atom experiment, throw stuff at it. Stuff's going to ping off of the nuclei, and they're going to be able to calculate where the nucleus is of each atom. So if they can calculate where this is and where this is, then they can measure how far apart they are. Okay. Now, what we're trying to figure out here is the radius of the atom. So if this is where the nucleus is and this is where the other nucleus is of two neighboring atoms, then we're going to cut that in half and say, okay, so that's not a perfect in half, that's fine. This is the radius of this atom and this is the radius of this atom. The problem is that that's not perfect because if we look, I don't know if I can trust myself to draw the same size line. If I drew the line kind of over here again, that actually doesn't get to the very end. So the radius that we calculate based on this experiment is actually smaller than in real life, but it's all we've got. And we're going to test every element the same way so we can still compare elements to each other. So we can figure out the radius of an atom, and then that's how we're going to compare the size of atoms to each other. Okay. You're not going to have to do this as an experiment. You're not going to have to calculate the radius. I'm just telling you where this information comes from. Okay. So the trend. Well, what we talked about between nitrogen and oxygen with the effective nuclear charge. Oxygen had an effective nuclear charge of 6. Nitrogen had an effective nuclear charge of 5. So oxygen was actually smaller because the effective nuclear charge was larger, which pulls the electrons towards the center more. So what we see is from left to right, atoms actually get smaller as we go left to right. So I'm going to draw an arrow this direction. And so atoms are going to get larger as we go this direction. Now, top to bottom, if we look at something like sodium, which has 11 protons, and then right below it is potassium with 19 protons. It's also, sodium has electrons on the 3rd energy level, potassium has electrons on the 4th energy level. So the more energy level something has, the bigger it gets. So atoms also get bigger as we go down. Okay. So the trend for atomic size follows this arrow. I'm going to draw a rough picture of the periodic table on the next slide, but it also is shown right here. Increasing radius, so for us increasing atomic size. So you can look at the red, the p orbitals on this, or I guess it's kind of orange. They definitely follow this trend. The boxes get taller as we follow these arrows. For the yellow ones, same thing. For the blue, which are the transition metals, the D, we kind of see some up and down and up and down and up and down. So what we're going to do, we're just going to ignore the D block electrons or atoms because they don't follow this trend. Notice the F block isn't even shown. Yep. So we're going to ignore those as well. So what I want to do here is let's change colors. I'm going to draw a rough sketch of the periodic table. Okay, that's the kind of the shape of the periodic table. And I'm just going to be, as we go through stuff, adding our trends onto this. So this arrow shows an increase in, I'm going to say neutral because we haven't talked about ions yet. Atomic, oops. So if you have your periodic table out, if you have a blank one that doesn't have stuff on it, or even if it has other stuff, I would draw this trend. Now I am going to go ahead and cross out the D block elements just because they're not going to follow this trend. Okay. So let's practice that. If you've got your periodic table out and you drew that arrow, we're going to just decide in each set of 3 which one is the biggest. I'm going to rank them. So on your periodic table, find lithium, find sodium, and find rubidium. All of those are in group 1. Okay, so for the trend, the arrow that we just drew, I don't care about the left to right arrow because they're all right on top of each other. What I care about is the up to down arrow, and it turns out that atoms get larger as you go down the periodic table. So the largest, so I'm going to say biggest to smallest. Of those 3, rubidium is the largest because it's the further down the periodic table. Next would be sodium, and last would be lithium. Okay, let's look at the other 3. We've got silicon, we've got chlorine, and we've got magnesium. These are all in different groups, they're all in different columns, but they're in the same period, they're in the same row, they're in the 3rd row. So we're looking at the left to right trend. So the trend, the arrow that I drew on the last slide, atoms get larger as they go to the left. So the largest one will be the element that's the furthest to the left, which is magnesium. And then next would be silicon, and the furthest to the right, which will be the smallest one, is chlorine. Last example, we've got beryllium, fluorine, and calcium. So these are not all in the same group or all in the same column. They're kind of, in different places. Well, so we're going to have to look at both the left to right and the up to down. So we're looking for the element that's the most to the left and furthest down to be the largest. So following that, calcium is the largest. And then we're going to go to the next element that's the most to the left and furthest down, so beryllium. And then the one that's not the most to the left or the furthest down, or the one that's most to the right and the highest, is fluorine. These are the types of questions I'm going to ask you to do with this. I'm going to give you elements, and you're going to have to rank them based on atomic size, or I could just say, okay, which one's the biggest, or which one's the smallest. So you're following that arrow. I will not give you elements in the D block in the transition metals, and I will not give you elements in the F block because they don't follow this trend perfectly. Okay. So the last thing in this video are what happens if they're ions. Okay, so if they're ions, they've changed their number of electrons, which means we can't use the periodic table anymore because their electrons are different, so their size changed because we changed the number of electrons. So when we're looking at ions, we cannot follow that arrow. That only works for neutral atoms. So if we scroll back, notice I wrote increase in neutral atomic size. Neutral was an important word that I wrote in there. So if the atoms don't have charges, like none of those elements there that are shown have a plus or a minus charge, so that's why we could use the trend. Well, if we're looking at ions, the change is going to, the change in size is going to have to do with the number of electrons, if we've added electrons or decreased the number of electrons. Thinking about just adding and removing stuff. So if I have a positively charged ion, so something that goes from a 0 charge to a +2 charge. Something has a +2 charge. Think about this. Are electrons being added or removed when something has a positive charge? So the correct answer is it's removed. It lost electrons. So if it goes to a +2 charge, it's lost 2 electrons. So just think about the size of an atom. If you take an atom and it's the way it is, and then you take out 2 electrons, just without thinking about chemistry, if you remove pieces of something, don't you think that should probably get smaller? Yeah, and that's what happens. So the reason why they get smaller is less about electrons are so big, so when I removed them it got smaller, and it's more about how that changes the effective nuclear charge. So what happens is if there's fewer electrons, the electrons are pulled towards the center more because the nucleus, the positive charge, overpowers the negative charged part of the atom, so they get smaller. So cations, positive charges, always get smaller than their parent atoms, the neutral atoms. Oops, I don't even know how I did that one. So electrons are removed, they're always the valence electrons that are removed, and so that pulls everything together because the electrons are not as repelled by each other as much because there's fewer of them. So flip it around. If something has a negative charge, goes to a -1, does that mean you added electrons or removed electrons from the atom if it has a negative charge? So the correct answer is you've added electrons. So you added another electron to it. So just again, thinking about it like you added a piece to something, it gets bigger, is how that happens. So negative charges, anions, get larger than their neutral atoms. And again, it's actually not so much because electrons are super big, so you add an electron and it makes it so much bigger. It's more that you add an electron, and now all the other electrons around it are going to have to back up because they're repelled by the new electron. Electrons are all negatives. They repel, they repulse each other. So when you add a new electron, all the electrons in their other orbitals are going to take a step back, which is then going to make the atom larger because they spread out from each other. So anions always get bigger. Okay. If we're looking at two atoms that have the same charge, or atoms that are all over the place, we can still follow the up to down trend. So ions do get bigger as you go down a group, down a column, but left to right, we don't have a specific trend for that. It's about the size. Okay. So if we have something like, in this example, an isoelectronic series, what that means is they're all in the same row and they have the same number of electrons. They have the same number of electrons because electrons have been added and removed. So the trend is, the more positive the charge, the smaller it is. The more negative the charge, the bigger it is. The more positive the charge, the more electrons it is lost. So it gets smaller and smaller and smaller each electron you take away. The more negative the charge, the bigger it is because you've added more electrons. So you add an electron, it gets bigger. You add another electron, it gets even bigger. Okay, so we don't have a left to right trend. We have a trend that is, well, I guess I'll just write it over here. So for ions, I don't have an arrow to draw around the periodic table. So for, really? Sorry, technical difficulties. Okay, buddy. I won't put my hand anywhere. Ions. That looks weird the way I drew that. Smaller in size to larger in size. The most positive to the most negative. So if I have an example of, let's do bromine, calcium. Wait, no, I don't want to do calcium. I want to do strontium. And arsenic and krypton. Okay, so if we look at these on the periodic table, bromine has 36 electrons, strontium has 36 electrons, arsenic has 36 electrons, and krypton has 36 electrons. So when I figured out the electrons, I took into account, like arsenic typically has 33 when it's a zero charge, but I added 3 more electrons because it's a -3. Strontium has 38 normally, but I took away 2 because it's a +2. Okay, so when they all have the same number of electrons. So in order to rank them, I'm going to have to look at my charge thing, because otherwise I can't rank them in any other way. So the most positive of these charges is strontium with a 2+. The most negative of these is arsenic with a 3-. And then we're just going to fill them in as we go. So if strontium is the most positive, the next most positive is krypton, which is a 0, and then bromine, which is a -1. Okay, I want to do another example. Sorry, I forget that I have a microphone on and I'm making noises. Let's do nitride, boron, sodium, and barium. Okay, so before I do my trend, before I rank them, I'm going to first figure out the number of electrons. That can help. So nitrogen is nitride, has 10 electrons. Sodium, sorry, I'm jumping around here, has 10 electrons. Barium has 54 electrons, and boron has 2 electrons. It starts with 5 and we took away 3, so it's left with 2. So before I do my charge thing, since I have electrons here that are not the same, if you've got a number of electrons that is super bigger than everyone else, you know, say 54 compared to 10, that's going to be the biggest one. I know it's not the most negative charge, but it's by far the most number of electrons. The smallest one, if you've got a number of electrons that is way smaller than the rest of them, say 2, that's going to be the smallest. So, took care of that one, took care of that one. These two both have the same number of electrons, but I've got to sort them, put them in the trend. So now is when we look at the charges. So the most negative one is going to be the largest. So between N3 minus and Na plus, N3 minus is the biggest, and Na plus is the smallest because Na plus is the most positive and N3 minus is the most negative. So this would be like kind of a tricky one because you do have to look at the number of electrons when you compare them, but our charge thing is how you compare them if they have the same number of electrons. And a lot of times, like the first example that I did, most of the time they're going to have the same number of electrons.